What kind of light bulb is in that projector?
Halogen?
It probably is halogen. Does anybody know why they put halogen in light bulbs? So when you run a lot of current through a filament, right, it gets it really hot, and usually it's tungsten metal that's in there. And the tungsten actually starts to boil and sputter, and little tiny bits of tungsten will fly off the filament and deposit on the outside of the light bulb, on the inside of the light bulb. Now, you've probably seen that happen, where the light bulb gets darker and darker before it burns out. One of the reasons it burns out is because the filament gets thinner and thinner and thinner over time as all these bits of metal fly off of it. They'll put halogen in the light bulb to block that. And the halogen gas will stop the sputtering of the filament, or at least slow it down. So that means they can run higher current through it, they can get it hotter, they can get it brighter. That's why car headlights are often halogen bulbs. So that very likely is a halogen bulb, but that's not the question I was asking. What technology does the light bulb use? How does it emit light? Why do light bulbs emit light? Now that happens to be an incandescent bulb. So that's one of the three kinds of light bulbs that we typically use. We use incandescent bulbs like that one. We use LED bulbs like that one nowadays, and I'm not even sure it's right to call them bulbs. And then we use fluorescent lights, which are those in the corner there, the indirect lighting. That's all fluorescent. I'm pretty sure it's fluorescent. Let me check that. I always carry diffraction gratings with me so I can check that. Let's see. Now you can tell if it's a fluorescent light by looking to see if it gives you spectral lines. And yes, those are definitely fluorescent bulbs. There's, looks like 3 or 4 different phosphors in those bulbs. There's different tuned bulbs there. Some of them are kind of reddish, some of them are bluish. So the people who have replaced those bulbs over time have not been particularly careful about which kind of bulb they put in there. But you can definitely see the lines. And that's definitely an incandescent bulb because the spectrum it puts out is just a pure continuous spectrum. That is too bright for me to tell. So I don't know, but I presume that's LED. There's another way to tell if it's an LED. Yeah, it's not hot. Right, so that's definitely LEDs. So how does the incandescent bulb work? Electrons running through a filament create heat. Why? Why do the electrons running through the filament create heat? Yes, the wire has resistance. What is resistance? What does it mean for a wire to resist the flow of electricity? It's math. Yeah, so imagine a piece of wire, right? And you magnify it so you're zooming really deep in on it until you can see the individual atoms. And what you will see there is this crystalline structure, usually a square crystal or a cubic crystal. And the individual atoms are nodes on the crystal, and they're all surrounded by electrons. And in a wire, the electrons that we're interested in are the ones that are pretty far away from the nucleus. Right, the nucleus will have a bunch of really close clustered electrons. We don't care about those. But then there's another set of electrons around the outside that are kind of loosey-goosey connected to the nucleus. And in the crystal structure, they're actually kind of free to wander around. They aren't really associated with any particular atom. There's as many electrons as there are protons, and they just kind of wander aimlessly, being moved around by any random electric field or so on. If you put a voltage across that, a really big electric field, well, then the electrons will move. And if you supply some electrons from a battery and take them out the other side, then they will move through the wire. Does anybody know the speed at which electrons move through a wire? It's roughly the speed that you can walk. The individual electrons themselves just kind of slowly plod through the wire. Now the signal The signal is a wave. This electron here bumps into this one, who bumps into that one, who bumps into that one, and that bumping goes at about half the speed of light. But the electrons themselves are just kind of, plodding through, because there's a lot of them and a lot of atoms. Now, as those electrons bump through the crystal, they cross regions that are nearer the nucleus and other regions that are farther away from the nucleus. And of course, they react electromagnetically with the nucleus, so they cause the nucleus to start to jiggle a little bit. Every electron that goes by makes the nucleus jiggle a little bit more. And if you put a lot of force on those electrons and try and shove them fast, then nuclei start jiggling around even more. And of course, that is heat. The jiggling is heat. So that's why the filament gets hot. Why does it glow? Why do hot things glow? You're glowing right now. You're glowing in infrared light. The human body puts off, 700 watts. So you are a bulb glowing in infrared light. We can't see that because our eyes don't receive it, but we do receive that kind of light. So why do hot things glow? And the hotter they are, the bluer they get. So yes, very good. It's electric charge oscillating. Why is the electric charge? So let's back off. That's a good point. Take one of the electrons in that wire, just one. And what's it doing? Well, it's bumping around across all those nuclei. Or take one of the nuclei. It's positively charged, and it's getting bumped by the electrons. Now you take a charged particle and you do that to it, you bump it, and the electric field around that develops waves. Right? The waves will propagate away at the speed of light, just because you're moving it. Well, an electromagnetic wave is light. The waves that you set up this way are simply photons. And the speed that you shake them is the frequency of the light that comes off. So the faster you can get those things vibrating, the bluer the light gets. And that's why incandescent light bulbs glow. I'm sure you didn't want to know that, but I had fun telling you. The talk I want to do today is some variation on the scribe's oath. This is a talk I've given a lot over the years, and it's a nice deep dive into the history of software and the history of programming. This is a fitting place for me to be talking about the history of software, since we're close here to where software was kind of invented anyway. Before we get into the history, let's talk about current events. Take a look around the room. Do a little demographic analysis of your own, and you will notice that there is a definite asymmetry to the population in this room. That asymmetry has something to do with age. I may be the oldest person here. I'm not sure about that. Is anybody older than 66 in here? I might be the oldest person. But that's not the most remarkable of the asymmetries in this room. The other asymmetry in this room, and at least one minority in that asymmetry is smiling ear to ear, is women. How many women are in the room? Oh, I can see 1, 2, 3, 4. Well, maybe that's all. I don't know. Maybe a couple more. Oh yeah, 5. Okay. 6. How many men are in the room? So what is that? What is it? What is driving that strange asymmetry? Now, it is the complete reverse of what it used to be. In the 1940s and the 1950s, the majority of programmers were women. Every single programmer on the ENIAC, the Princeton computer, one of the first electronic computers, every single programmer on that machine was a woman. The first person to write a compiler was a woman. She actually coined the word compiler. That was Grace Hopper who did that. When I was a young boy, about 18 years old, I went to work at a place that had a computer. I was writing assembly language code and COBOL, God help me. They had about 30% women, about well, 70% men. And they were all old. Well, of course, they all looked old because I was 18, but they were all in their 30s. There weren't any 20-year-olds. They're all in their 30s or 40s. They're all generally mature, and men and women, and about a 70-30 split. And then in comes me and my buddies from high school, and we're all 18 and bubbling with energy. But that was my experience at my first programming job. Within 10 years, I was working at a company that had 50 software developers and maybe 2 or 3 were women. So something happened in that decade. And this is the decade of the late 70s, early 80s, probably. And what was it? What happened? Now, when we look at the demographics, where is it that the women are, how do you say this, being filtered out, if they're getting filtered out? There's something is going on. Something is either removing women from the chain, or women just aren't entering the chain, and it's not exactly clear what that is. What we do know is that there are far fewer women going to university to study computer science. It's not just at the employment boundary, it's at the university boundary. We don't know if it's before that, could be at the high school boundary, don't know. But what happened? Now you have to be careful, because if you say the wrong thing, you can be fired. Right? So you must not say the wrong thing. And that's a frightening thing in the Western world, to suddenly be confronted with the notion that there are wrong things that you can say that may or may not be true. It doesn't matter. But if they are wrong, you can be fired by a company like Google. So don't answer yet. Think carefully. Notice how everybody got quiet on that one. Oh, shit, he's going to talk about James Damore, isn't he? So, before I get myself into more trouble, let's talk about ancient times. If we go back several thousand years, there was a civilization, and it worked pretty well. The Egyptians had a pretty good civilization. The Assyrians had a pretty good civilization. The ancient Hebrews had a pretty good civilization. There were a number of civilizations that seemed to come up almost from nothing. They were obviously agricultural. They built cities, they built pyramids, they did all kinds of very interesting things. They had wars, everything that normal civilizations do. And there were certain people in those civilizations that had a skill. It was the skill to read and write, and the skill to manipulate numbers. They were the scribes. The scribes understood bizarre squiggles made on parchment or on clay. They hid their knowledge from everyone else. They did not want this knowledge to spread. They had strange rituals and costumes, and they were extremely well regarded by the governing officials, because the governing officials understood that nothing could happen in their civilization if it was not written down and recorded and then read back. No law could be passed, no law could be created, no law could be enforced without something being written down about it. No transaction, no monetary transaction could take place unless it was somehow written down and recorded. So the scribes became extremely elite, to the point where they were exempt from fighting in wars. No scribe had to fight a war in ancient Egypt, for example. And they often did not have to pay taxes. We should talk about this. Right? They had this skill. It was the skill of reading and writing bizarre squiggles that other people didn't care to have. The majority of people in that type of civilization didn't need to read. Didn't need to write, didn't need to read. They could get by just fine by, walking behind an ox and plowing a furrow or hammering on stones. And there were lots of jobs to be had. Fighting, that's another good one. You could be a soldier. Right? Didn't need to read. Only a few people did. These people had deep rituals. Let me describe one of the rituals that the Hebrew scribes had. It's particularly fascinating. These people, their jobs, among other things, was to copy the Torah, copy the Bible. And so they had rules about this. Right? First of all, every page, and they did divide them into pages, every page had to have a certain number of columns and a certain number of rows. Right? And it had to fit within a certain dimension. The making of the parchment, there were strict rules for how you made the parchment. There were strict rules for how you made the ink. All of that was, deeply secret and covered. Then when you copied a page, so you take a page that was old and you were going to copy it, you had to copy it by saying every word out loud. You must utter the word. So each word is uttered as you are writing it. But if you are about to write the name of God, which was 4 Hebrew letters, YHWH, they translate to English, sort of. Right? If you were about to write that, you had to stop and then go wash yourself. Take a bath, wash your body and your clothing, and then come back with a brand new ink and pen and write the name of God, and then go wash yourself again, and then come back. When you were done with a page, they did an analysis. They said, okay, count the letters on the old page, it must equal the number of letters on the new page. Count the words on the old page, must equal the number of words on the new page. Count the sentences on the old page, must equal the number of sentences on the new page. Count the paragraphs, must equal the same. Find the center word, the word that's exactly in the center, and it must be in exactly the center of the other page. They didn't understand about CRCs yet. But it was a pretty good checksum, right? Pretty good checksum. They were allowed to make 3 errors, which they could correct. But if they made any more than 3 errors on a page, they discarded the page, but they did not throw it away. They put it in a special jar, and that jar was then stored in caves, never to be used because it was in error. The demons had accosted it or something, but never to be destroyed either, because that would be sacrilegious to the words that were on the page. It's a very good thing they did this, because many of the scriptural scrolls we have found were in those jars. The discarded pages. The Dead Sea Scrolls, for example. The discarded pages. Did I mention they didn't pay taxes? We come to the modern day, and here are you and I. And you and I understand, are able to read and write bizarre squiggles on something. LED lights nowadays. But we understand those squiggles. There are other people who don't understand them and don't want to understand them and have no need to understand them. You and I do understand them. And our civilization depends for its existence on our ability to write and read those words. Now that's a bold statement. Is that true? How dependent is our civilization upon you and I? Well, how much software is running in this room at the moment? How many computers do you have on your body at the moment? He's got a bunch. How many do I have on my body? Well, that one's a computer. There's definitely computers on me. I've got my iPhone. How many processors are in this iPhone? There's graphics processor, there's the main processor, there's GPS processor, there's the cell phone processor, there's a battery in here, that's got a processor, there's another battery in here, that's got a processor. I don't know how many processors in here in this thing, but there's a lot of them. What else do I have? Well, I got my iWatch, Apple Watch, processors in that. AirPods, how many processors in here? Get one headphone, there's one in there, there's another one. And the case has one, at least one. My body is literally covered with processors. Look at the walls. How many processors are in the walls of this room? Now, there's switches over there. I don't know if there's any processors in those switches. It seems unlikely to me, but it's possible. There's a box next to it. What would you have to guess? If you had to guess, is there a processor in that box? I don't know. Oh, don't push that button! He's going to probe it. The clock back there. Is there a processor in that clock? There almost certainly is a processor in the clock, because nowadays it's just too easy to make a crystal clock. And what a crystal is a little piece of quartz that they get vibrating by running a current through it, and then they count the vibrations with a little computer. And they usually try to get the crystal balance to something like 32,768 cycles per second, which is a number, of course, that you know. Let's see, how about that exit sign back there? Is there a processor in that exit sign? It's got a battery in it. Battery has to be charged. Nowadays, we tend to charge batteries by getting a little digital signal processor and trickle charging them and measuring the voltage so that we don't get memory effect or runaway burn. Right? We don't like those. Thermal overloads. What else do we have here? There's a speaker somewhere. I don't know where the speaker is. It's back there. It's probably a processor in that. So the room, there's processors running in the room, hidden in the walls and just around us. Go out on the road. How many processors are in a modern car? How many lines of code are in a modern car? Modern car, and not a Tesla. Forget about a Tesla. That's a whole different matter. Right? A modern car has around 100 million lines of code. And at this point, all of you should be going, 100 million? Now, most of it's in the entertainment system and the GPS system and stuff like that. But there's a fair bit of code that sits right in the engine and controls the engine, especially if you have a fuel-injected vehicle. Right? And do you believe that when you touch the brake, that there is a cable that goes from the brake pedal to the calipers of the brake to squeeze the disc or the drum and stop the car? Do you believe that's true? It used to be true. Nowadays, that's not so true anymore. You touch the brake and it sends a signal to a processor, and then the processor decides whether or not to stop the car. There are if statements in there. And that should fill you with a certain amount of concern. The same is true of the accelerator pedal. You touch the accelerator pedal, that's not opening a butterfly valve on a carburetor anymore. That's going right to a little processor. And that processor is going, oh, he wants more fuel. And he increases the frequency rate of the fuel injectors. How many people have been killed by that software going mad? Dozens, not hundreds, dozens of people have been killed when the software in the motor control of the car lost its mind and the car accelerated out of control, didn't obey the brakes, didn't obey the accelerator pedal, could not be turned off, and people get injured, they get killed. There was one terrifying cell phone recording of a guy whose car was just completely out of control. He was zooming down the motorway. He calls the police saying, I cannot stop my car. I don't know why. I can't turn it off. The brakes don't work. It's accelerating at full speed. Can you please get the toll gates open and follow me? And of course they couldn't follow him because he had a Maserati of some kind, running down the road at some crazy speed. He actually had to run out of gas. Now he was one of the lucky ones. Toyota had to pay out a rather large penalty from a judgment because of a software failure in their cars, or they killed a number of people. An interesting failure mode too. Do we have any embedded programmers in the room? Writing the embedded code and microprocessors and stuff like this? Okay, so you'll know what I mean by this. In the old days, it's also true today, but less so. If you had multiple threads running in an embedded system, you had to allocate stacks for those threads. Right. And you had to measure how big should those stacks be, but you didn't have a lot of memory in those days, so you tended to kind of play the game, you know, should it be 100 bytes, 150 bytes, can I get away with 125? They did the math wrong, right? And at some point there was an interrupt at just the wrong place and the stack depth was already too low and it went over the limit, and of course there's no memory protect on those machines, so it couldn't detect it, so it corrupted a block of memory that didn't belong to it, but it did belong to the process that controlled the accelerator and the brake. Note to future self, do not put the accelerator and the brake in the same process. And the car went off, it lost its mind. You and I belong to a discipline that rules the world. We don't know we rule the world yet. Nobody quite really understands that. But we do. We rule the world. Other people think they rule the world. And then they hand the rules to us. And we write the rules that run on the machines that do everything. Think about your grandmother if you still have a grandmother. Your grandmother cannot avoid interacting with the software system on literally a minute-by-minute basis because you can't do anything in our society without interacting with a software system. You can't watch TV. You can't make a phone call. You can't use the microwave oven. You can't wash dishes or your clothes. You can't drive a car. You can't buy anything. You can't sell anything. You can't get insurance. You can't make an insurance claim. No law can be passed. No law can be enforced without a software system being in the middle of it. You cannot vote. You cannot even commit a crime. Well, maybe some. The point is that virtually every waking moment of our lives, of everybody in the Western world, is in interaction with some software system somewhere. And many of us interact with software systems in our sleep. Anybody put their phone beside them and measure the body motions so that you know what your sleep cycle is? How much money's been lost by stupid software bugs? Yeah, stupid. Well, because there are intelligent software bugs, but I mean stupid ones. So, an awful lot. There's been a lot of strange bugs that have cost a lot of money, and there's the obvious ones like the Ariane 5. Is it kilograms or So they metric English system screw ups. That's happened more than once to a spacecraft, where the spacecraft is completely lost, $1 billion spacecraft. Oops, didn't convert properly, sorry. There was a trading company called Knight Capital. Anybody heard of that one? And it was just some poor idiot software guy who did some wrong thing. It was actually a team of people who did the wrong thing. And through a chain of events, they managed to lose $450 million in 45 minutes. Right? That's pretty fast. Okay? And the CEO woke up the next day without a company because the vultures had already bought it out from underneath him. There will come a moment when you and I, someone in our industry, will do some stupid thing and manage to kill 10,000 people in a single stroke. Yeah, like the 737 MAX thing. Is that a software bug? Is that a bug? Or is it a design issue? It's a software fix, oddly. They think they can fix it all with software. Where have you heard that before? They think they can fix the thing with software. Does that imply that it was a software bug? And how responsible are the programmers for that failure? What is society's take on that? How will society treat us as we kill more and more people? Something serious to think about, something that I think I'll come back to. But before I do, I want to go back in time. We're going to go back, way back to the 1940s. There's a little blue arrow, that's where I was born, 1952. So we're going to go back before I was born. Back to this moment in time. This is Alan Turing's very famous paper. Who's read this paper? You've read it? Ooh, good. There's people in here that have read Alan Turing's paper on computable numbers with application to the Einsteidungsproblem. Well, that's a compelling title, isn't it? What was going on here? Well, Turing was a kind of a mathematical genius. And there was a problem that was originally stated by David Hilbert, the famous mathematician. He put out a challenge to the mathematical community to solve the decidability problem. That's the Einsteidungsproblem, the decidability problem. What is the decidability problem? Well, there are a number of equations in integers. They're called Diophantine equations. They're integers in and integers out. And what Hilbert wanted to know is, given a particular equation, could you prove that it has a solution? He didn't want the proof. He wanted a process to tell you if it could be proven. That was the decidability problem. Could you prove that all equations, all Diophantine equations, can be proven? or given a Diophantine equation, can you prove that it can be proven without proving it? They got really weird back in those days. So that was what Turing set out to do. And he stumbled across this idea, manipulating integers. And the idea was he could build a little machine that would manipulate integers. There's a little machine that would make marks on a tape, and he could move the tape back and forth. And a human would operate it. There was no electronics involved. Nothing really very interesting about the machine. The human would make little marks on the tape, and the human would move the tape back and forth, and the human would read the marks on the tape and follow a set of instructions. So it wasn't an automatic machine in any sense, at least not the way he described it. And then he went on to show that you could come up with a set of instructions that could be turned into numbers, and those numbers could be put on the tape, and the human could still be operating it, but now the human has no idea what the human is doing. They're just following these blind instructions while these numbers come in from the tape, and those numbers are now executing another program. And he goes on to show that you could compute all kinds of numbers. Lots and lots of different kinds of numbers. He could compute all sorts of infinite strings. He could compute 1/3 to an infinite level, right? He could compute pi or e to any level he wanted. And then eventually he proved that there were certain numbers that you could not prove would stop. Certain programs, and every program was a number. You could not prove that it would stop. And that was the basis for his deciding that the decidability problem was false. There are numbers that cannot be computed. There are infinite strings of digits that no algorithm can compute. Now that was, wonderful. Okay, great. And he was not the first person to solve that problem, but he was one of the first. The other person who did solve the problem and who solved it within a matter of days was Alonzo Church. Some of you may have heard of Alonzo Church. He's what we would call now the founder of functional programming. Alan Turing we would call the founder of procedural programming. Well, what does all this have to do with programming? Well, so Turing, in order to do this, in order to build this proof, had to come up with a programming language. And it's remarkable. If you read his paper, he literally invents macros, subroutines, loops, if statements. He invents everything that you and I are used to in a kind of bizarre language, but still, it's everything you and I are used to. He invents it all in this one dumb little paper. If you want to dive into this paper, by the way, there's a very good way to do it. Charles Petzold wrote a wonderful book on this. Who's heard of Charles Petzold? Okay, this is the guy who wrote all the MFC books in the 80s, right? All that C code that was in the Microsoft Foundation classes, all that C++ code later. Well, he wrote all those books, and then he got tired of writing MFC books, so he wrote this lovely book called The Annotated Turing. And in The Annotated Turing, he presents the entire paper, paragraph by paragraph, surrounding it with the history and the motivation and explanations and so on. So it's a very, very good way to get an idea of just exactly what was going on in this guy's head and what kind of genius he really was. Now, of course, he got involved in World War II and the breaking of the Enigma code and so on. I'm not going to get into an awful lot of that. The kind of devices that he was using in those days were these kinds. That's a relay. That's just an electromagnetic coil. And if you energize the coil, it'll pull this piece of metal in, and that'll move these switches here. So you could switch current back and forth by energizing coils and so on. Nice. And he had these nice little stepper rotors. And they had, little switches in them as well. And he was able to use the theory of his Turing machine as a way to figure out how to use devices like that to very rapidly search through the Enigma codes, looking for patterns. And that was a big way of winning World War II. He wanted to use these kinds of devices. These are vacuum tubes. Anybody seen a vacuum tube? Some of you have seen vacuum tubes. Some of you probably have not. Those of you who are younger than I may have never seen a vacuum tube in your life. These are vacuum tubes. Vacuum tubes are very fast. very fast switching time. You can get a vacuum tube to switch several million times a second, whereas a relay will only switch about 10 times a second, so big advantage. The problem with vacuum tubes back then is that they were made in very small quantities and they weren't very reliable and you couldn't get them to be repeatable, and then the filaments all burned out and it was just a nightmare to use them. So trying to get a circuit with 50 or 60 vacuum tubes working was a nightmare. So it took them a long time to actually try and get a vacuum tube machine up and running. Towards the end of the war, they actually did, but it was kind of too late at that point. But nevertheless, after the war, they kept on working on this problem, and they built this lovely machine. This is the automated computing engine, the very first electronic computer ever. And Alan Turing was the very first programmer of this machine. Other people programmed it too, but Alan Turing was the first. He actually designed the kind of a processor, the instruction processor, and so on. This is an interesting machine. It had an add instruction, but no subtract instruction. Turing actually didn't even want the add instruction. All he wanted was logical OR and NOT. And from there he could construct addition and he could construct subtraction. But other people in the team said, no, we got to at least have an add instruction. It took a whole bunch more circuitry to do that, but okay. And Turing was angry about that, but he didn't win every battle. And it had 22-bit words. And the 22-bit words, it had 1,000 of them, 1024. 22-bit words. Where did they store the memory? Well, the plan was to store the memory in these things. These are big tanks of mercury. And what you'd do is you would get a speaker on one side and a microphone on the other side. And you would take the bits, and you'd use the bits to push on the speaker, and an acoustic wave would move through the mercury, and you could hear it with the microphone on the other side. Then you'd wrap it around and put it back in, so it was kind of a disc. Right? The bits would go through like that, and they would move at the speed of sound in mercury, which is pretty fast. So that was where they would store their data. The problem with those was that if a truck went by, it kind of shook, you know. So they actually ended up not using those, and they used this. And this is a CRT memory, a cathode ray tube. So, who's seen a cathode ray tube? Yeah, several of you have seen. Who's used one? As a terminal, right, on your computer. Good, okay. Nowadays, you know, I don't even know if you could find a cathode ray tube. But in those days, they were fairly common. And it turns out that if you take the electron beam and you sweep it at different parts of the screen and you let the intensity get bright, it will deplete the charge on that screen there. And then you can sweep the beam over it again and detect the fact that the charge has been depleted. So it's a kind of memory device. The memory didn't last really long, but you could refresh it. So that was what they used. And this had the extra added benefit that it was an output device. This is where Alan Turing read the results of his programs, by actually looking at memory. Now, you think you look at memory when you type a command in and say, dump memory on this. No, he was looking at memory. Cool, and it's little dots, right? Little dots, on and off dots. He grouped the bits into groups of 5. He used base 32. Didn't use base 16, didn't use base 8, not octal or hexadecimal. He used base 32. Very efficient. He had to have 32 symbols, so he borrowed some of the English alphabet for that. He wrote it right to left for some strange reason, probably because that's how you read it off the screen. So he wrote it backwards, and he used base 32, and he wrote programs that calculated floating point numbers. Has anybody here written a floating point package in assembly language? In a machine that only has an add instruction? That can only add 22 bits? That's not a trivial challenge, right? He had to first even imagine a floating point number. You've got a machine, right? And that machine can deal with nothing but integers of a certain size. And he had to imagine what a floating point number was. And then he had to work out all the bit manipulations so that he could do multiplications and divisions and additions. By the way, addition is the hard part in floating point math. Not multiplication and not division, because those are simple. You do addition, that's hard in floating point math because you've got to get the exponents lined up, and it's really difficult. He did all of that stuff. He invented the concept of a subroutine, a real subroutine. He had subroutine-like things in his Turing machine in that paper, but here it was a real subroutine. When they invented the machine, they didn't think about storing a return address, with a call instruction. They didn't think about that. They had jump instructions, so you could transfer from one part of memory to another. You could jump. But they never thought about saving the return address, so Alan Turing had to invent the idea of saving the return address, pushing it on a stack. He invented the concept of a stack. He wrote the first stack code. It's really fascinating. Yeah, that's what I just said, all that stuff. Now, here's where it gets really interesting. After a year of all this, and he's writing more and more interesting programs. And what are his programs doing? He's calculating numbers. He's interested in numeric stuff. He's calculating the arctangent of some crazy thing. He just wants to calculate. But at the end of all of this, he writes a paper for the university. And notice what he says here. We shall need a great number of mathematicians of ability. Are you a mathematician of ability? Because there will probably be a good deal of work of this kind to be done. How did he know? Even then, after a year, he said, we're going to need a lot of people. Because this is hard. Yeah? And then he went on to say, one of our difficulties will be in the maintenance of an appropriate discipline. So that we do not lose track of what we're doing. Now that sounds like it comes from experience. Not much has changed, unfortunately. We still need to maintain an appropriate discipline because we often lose track of what we are doing. Fascinating that within just a year of working this way, he was able to come to those conclusions and make a prediction about something 70 some odd years later that is truer now than it was then. Mathematicians of ability, a great number of them, appropriate discipline, that's going to be a theme here. How many computer programmers were there in the world in 1946? And it was one, or big O of one, because it was more than one. First Alan Turing, and then a few other guys, and a few other guys after that, but big O notation of one. The number of computers in the world was one. The number of programmers in the world was one, or big O of one. 1946. How long ago was that? 73 years. Less than a person's lifetime, most people. There are people alive today that were born before that event. Not many. Things started to change pretty fast. By the 1950s, that whole CRT memory thing was out the door. That was inefficient and ugly, and you really couldn't get an awful lot of bits. You'd need a lot of screens. So they started to think about different ways to store bits, and one of the ways, the most popular, turned into this core memory idea. Has anybody worked on a machine with core memory? Look at that, see, we got some oldsters in the room. Not many. And everybody's going, what? Core, what? And, oh, by the way, you've seen the word, haven't you? Core. That file that gets created when Unix processes crash. Now you know why it's named that. That was the dump of core. We used to call it that. What's in core at the moment? We'd literally walk up to a computer and say, what the hell's in core? We didn't say memory. What's in core? What is a core? Well, it's these little rings. Right? And these little rings, by the way, I own this core plane. This is mine, and I took this photograph, right? So these little rings are made of powdered iron mixed with clay, molded into a ring shape. It's called ferrite. And then they are woven into this fascinating pattern here. Now, this is magnified, but these rings, that's about 1 millimeter. They're tiny little things. This is the core plane here. And you can see they're arranged in a kind of a matrix, a square matrix. There's 16,384 cores on that one matrix. That's 16K bits. and then they would you'd stack those planes up. So if you had a 12-bit machine, you'd have 12 of those planes, and you'd have 16K bytes. And then they'd add one more plane for parity, because they didn't trust this, with good reason. It was reliable, sort of. Right, those magnetic fields are really small. Then what they'd do is they'd run current through these wires. Now, if you've studied magnetism, you'll begin to understand this. You can change the orientation of a magnetic field if you assert enough magnetic force on the material. If you assert less magnetic force, then the magnetic field will not quite flip and it'll snap back. But if you assert enough force, it'll flip over. So how do you do that? Well, you run half the current that you need to flip a core through that wire. You run the other half of the current you need in that wire. The only core that receives enough of an impetus is the one that's at the intersection. So they could flip individual cores just simply by running the current through in the right direction. If you wanted to write a 1, you had to run the current through that way. And if you wanted to write a 0, you had to run the current through that way. Or something like that. How did you read it? Well, you read it by writing it to a 0. If you wrote it to a 0 and it was already a 0, it wouldn't flip. If you wrote it to a 0 and it was a 1, then it would flip. And when it flipped, the flipping of that magnetic field would induce a small current on another one of these wires. And there's a little amplifier at the end that would say, "Ooh, I got it." And then you'd write it back into memory. So it was a two-step process. To read the memory, you had to write it to 0 and then write it back in. And you could do that a couple of million times a second. These things will flip fast. Better than that, turn the power off in the computer, those magnetic domains stay. So that's what we would do. We would put lots of software in our computer and we'd load it all up and then we'd turn it off. Then we'd go get lunch. Then we'd come back and we'd turn it on. It's all still there. And then we'd continue to work. Yes, I know, silly machine. In the 50s, the production of vacuum tubes got better. They became smaller, became more reliable, they became more repeatable. They could crank out the same vacuum tube over and over and over again. And the idea of assembling thousands of them together became possible in some kind of mass assembly regime. Now, the amount of circuitry required to control just one tube, you would have to hold in, something that's roughly this size. I wonder what this is. It says pusher on it. It's got a USB plug on it. I bet it's a little disc. It's a little disc? Is this a little disc? Or maybe it's receiving my microphone signals or something. No. No, I'm not going to do that. But this would be the kind of size of the circuitry you would need to control one tube. So if you have 1,000 tubes, you need 1,000 of these. And they generate a lot of heat, so you can't pack them really close together. So they would actually put them in vaults, and you could walk into the vaults, and they would have hallways in those vaults, and you would see these cards with tubes in them stacked into the vaults. These machines were really big. And Fortran was invented almost immediately. Fortran was invented in 1952. I say 53 up there, that's when it finally got passed as a standard, but the actual standard was submitted by John Bacchus in 1952. That's the year I was born. I am slightly older than Fortran, just a little bit. That's Fortran code. Has anybody written any Fortran? Oh, look at that. Look at people who've written Fortran. Fortran 4? 7. You mean 77. That's 77. Yeah, okay, fine. Yeah, I'm getting some Fortran 4 people. Anybody written Fortran 4? See, even that's too modern. This is Fortran. They didn't even have a number. Right, this is just Fortran. And I want you to look here. Thank you. Yeah, look there. Said I did screw something up, didn't I? Okay. I want you to look there. You see these if statements? Now, that's a real if statement. Honest to God, that's an if statement. They realized they needed the word if. And then in parentheses, there's an expression. And the expression you understand, right? IB plus IC minus IA. Why the I? It's an integer. Any variable that began with the letters I through N, which are the first two letters of the word integer, was automatically an integer. Every other variable was a real number. How many letters could you have in a variable name? 8. 6, you might be right. Might be 8. No, it's 6, you're right, it's 6. Has anybody read clean code? Did I ever tell you to use 6 letters? Yeah? What your name should be 6 letters. Can you imagine trying to come up with meaningful names when you are restricted to 6 letters? It's actually worse. It was not restricted to 6 letters. It would just look at the first 6. You could have a name as long as you wanted. If IB plus IC minus IA, and then if that's negative, we're going to jump to 777. If it's 0, we'll jump to 777. If it's positive, we'll jump to 799. Now, what are those numbers? Well, those are line numbers. Well, no, they're not line numbers. They are numbers that you put on the front of a line. But there was no rationale for how you put those numbers on the front of a line. They did not need to be in order. They did not need to be in sequence. It was just a number that you put on a line. And you can see them here. Here's line 799. Here's line 601. No necessary order to it at all. It was just a label. Now, why didn't they use a name? You know how much a bit cost in those days? One of those core bits, they're well over $1 a bit. Right? A 4K by 8 stack of memory was hundreds of thousands of dollars. Memory was precious. Anybody got a thumb drive in their pocket with 64 gigabytes in it? That's $64 billion. Right? So yeah, they didn't want to use labels. They didn't want to use names because names take up too much space. 1 byte per character. They just used an integer, and that of course would just be 1 word. Saved a lot. Now, how did we write that code? Well, we punched it on cards like this. Anybody seen a punch card before? Oh, look at that, yeah. Everybody on that side of the room. Huh. So, and if you look on the top, you'll see that the code is actually written on the top in a dot matrix form. And then the code is punched into the card that way, and we would write the code on cards. But no, we didn't actually write the code on cards. The programmers wrote the code on these things. These coding forms. Programmers in those days did not use keyboards. We did not know how to type. That was for someone else to do. We were programmers. We wrote the code. Other people punched it. We would write our code on these sheets of paper. And then after we had checked it very, very thoroughly and used the only editing tool we had, which was an eraser, we would then take a batch of coding forms and we would walk them down the hall to the room where the key punch operators worked. Now, the key punch operators, imagine a room like this filled with 20 machines, one person sitting at each machine, and they are busy punching cards. They're looking at data and they're punching cards, and they're very good at it and they're very fast. Now, what are they doing? They're punching data. Why are they punching data? Because the only way to get anything into the computer was on card. There was no network. There was no magnetic tape. There was nothing else. The only way to get data into the computer was on cards. So anything that went in had to go on cards. Employee reports, time cards, bill of material stuff, general ledger stuff, it all had to be punched on cards. So these people were busy. Programmers would walk into that room with extra work for them to do. They hated us. I walked into a room once, I was 18 years old. I walked into the room and I was looking around. Where do I put my program? Because it's the first time I'd been in there. Where do I put it? And one of the key punch operators looked at me and said, "Flutter away, little butterfly." It was the last time I went into that room. I learned how to type. I went down into the basement and I taught myself how to punch cards, and I punched every program I ever wrote after that because I wasn't going to go back into that room. Most of the programmers, however, had a better relationship with the key punch operators, and they would get their deck a day later. They go back a day later and, oh, there's the deck sitting there and rubber band around it with their coding forms with it, and they take it back to their desk, open it up, and look through the cards. You have to check them because the key punch operators had no idea what they were punching. They just punched. So you'd have to look and make sure that it was punched correctly. It never was. So there was a key punch machine in the programmer's room, and you can edit your cards on that. Editing a program on cards is fun because you have to duplicate it right up to the point of the error and then type the extra code, extra stuff, and you don't want to know. Eventually you get your deck into a state where you think it's compilable. You're writing COBOL or Fortran or PL1 or some language like that. You might be doing assembly language too. And you finally get the deck to where you think it's compilable. You've checked it in your head over and over again. Put a rubber band around it. Put your name on the top with a magic marker. And then you walk it down the hall to the computer room. Programmers were not allowed to touch the computer. We were not allowed in that room. The only people allowed in the computer room were the operators. The operators governed the computer room with a steel fist. There was a combination lock on that door. They were the only ones who had the combination. If you wanted to get your deck of cards into that room where it could be compiled, you went to the door and you waited for them to acknowledge you. There was a little window. And then they would tell you to back up. And you backed up. And you left your deck on a little table outside the door. And then they would unlock the door and a burly, hairy arm would reach out and take your deck into the bowels of the computer room where it would sit until 3 in the morning. It would sit until 3 in the morning because the operators had a hell of a lot of work to do. These machines were multi-million-dollar machines. They had to be executing all the time. Every microsecond was important. And so they were constantly running jobs and running, general ledger jobs and manufacturing jobs, all these jobs. At 3 in the morning, they finally got all the jobs done. And they took all the programmers' decks and they stacked them up on the card reader and they pushed a button and they all went to have coffee. And printouts would come. They would rip the printouts off. They'd put them on a table outside the computer room door. The next day you'd walk in, there would be your listing on a table. You'd take it back to your desk. You'd open it up. Your deck of cards is with it. And you look in there and you realize you forgot a comma. This was the life of a programmer in the late 50s, early 60s. Right? And so in order to get anything done, you had to work on 10 programs at the same time. Right? So you'd finish one, you'd finish setting one over to the computer room, then you'd do the next one, you'd send that to the key punch operators, and then you'd look over the next deck that you got, and you'd fiddle with that, and you'd set that to the computer room. So you were in a constant assembly line of programs. It was the only way to get anything real done. This is when Lisp was invented. 1957, 1958. Lisp. Lisp is the language that refuses to die. We've tried to kill it. It keeps coming back. And that tells me something. I believe all the others will eventually die. And all there will be is Lisp. The machines looked like this. That's an IBM 708, 709 vacuum tube machine. You don't quite get the idea of how big this machine was. You're only looking at the front panel. Notice who's operating it. These machines were really expensive. They made 140 of them. Not a lot. They were sold to defense laboratories, weather laboratories, government institutions. Very large companies might buy one. But they were well out of range of normal people, normal companies, even big companies, well out of the range. They were difficult to program, difficult to maintain. Who was programming? Well, a lot of these people were. This is Grace Hopper. This is Grace Hopper here. She eventually became the, what we would nowadays call the CTO of UNIVAC, but they didn't call it CTO in those days. She was the VP of engineering. And she was teaching a bunch of kids here how to use the UNIVAC machine. You can see her teaching over there. That's a much earlier picture of her. This is the woman who invented compilers. He coined the word compiler. This is the woman who designed the COBOL language. Any COBOL programmers in the room? No, see, because most of us didn't survive. These are the programmers of the ENIAC. The ENIAC, fascinating machine. All right, here you get a real good idea of what these vacuum tube circuits looked like. Right? And the ENIAC was a fascinating machine to program. You did not program it in code. You programmed it with wires. There were sockets that pulses came out of, and then you would wire them up to adders or deciders or subtractors or other things, and you would chase these wires around, and every instruction was another batch of wires. Really difficult stuff. And these are the people who were programming those machines. The men didn't think that was worth their time. The men built the machines. The women programmed the machines. Programming in those days was considered a clerical job. Where did the word computer come from? People who did adding. Not just people, women. Women who did adding. Back in the 1800s, if we needed to do a bunch of math for artillery tables or for anything else where you needed a lot of math, we would get a bunch of women in a room. We called them computers. And we would say, okay, these are the numbers you need to add for us. These are the calculations you need to do for us. And they would just do calculation after calculation. We eventually gave them adding machines, right? So they could do adding machines. Who saw Hidden Figures? The movie Hidden Figures. That's the last vestige of that era, where those people were the computers who were doing the computations that were necessary. And then these became the computers, these machines. We've gotten all the way to 1960. Now, how many years has it been? Right? It's been 14 years since 1946, 14 years since Turing. Already fascinating things have happened. The number of computers in the world is over 100 now. Probably 200 or 300, because IBM was not the only company making them. But probably not 1,000 yet. The number of computers in the world was still less than 1,000 probably. How many programmers were in the world? Probably well over 1,000, probably close to 10,000. Why? Because in those days, in order to keep a computer busy, you had to have at least 10 programmers. There were no operating systems, there were no frameworks, there were no subroutine libraries, there was no code out there that you could download. Any instruction that executed is an instruction that you wrote. And so there was a tremendous amount of work to be done, as Alan Turing said, and it just took an awful lot of people to write the code to keep those machines running all the time. And they had to run all the time. You couldn't justify having a computer if it wasn't running every microsecond. So there were a lot of programmers, not as many computers. What were those programmers like? Well, you couldn't go to school to be a programmer in those days. So who did they get to write the programs? Well, they found engineers and mathematicians and scientists and people who were technical and interested, and they were old. They were in their 40s, they were in their 50s, maybe they were in their high 30s, but they were already professionals. They already understood business. They understood schedules and deadlines. They had been in business for a long time. They were recruited by their companies to solve this horrible but fascinating problem of getting these machines to work. But the transistor was already invented, and it was coming fast. The transistor was a fascinating device, just like a vacuum tube. It could switch current really fast, but it didn't generate any heat, and it didn't need a filament. And the amount of circuitry you needed to support it was very small. And so the machines began to shrink, and they began to shrink really fast. And the amount of power you had needed to power them went way down, and the reliability of the machines went way up. By 1965, IBM had produced 10,000 of these machines. These are 1401 machines. 1401 is a fascinating machine. It would ship with 4,000 words of memory, not 4096, 4000 in decimal, because they used binary coded decimal as their math. IBM had made the decision that business people were going to use these machines, and therefore everything should be done in decimal. So all the arithmetic circuitry and all of the memory circuitry was done in binary coded decimal. Does anybody know what BCD means? Binary coded decimal? Yeah, okay, 4 bits, and you only used 10 of the combinations. 10,000 of those. You could rent them for $2,500 a month. That's about $20,000 in today's dollars, but that put it in reach of small businesses, mid to small businesses. You could get one of these machines. Now, you also needed a stable of programmers to run it, but it put it in reach. You could actually have one of these in your office. And, you know, lots of people thought, well, that's a great idea. And so IBM made a fortune selling these things. And the number of computers in the world went up. There were now tens of thousands of computers, probably pushing close to 100,000. The number of programmers in the world went up, hundreds of thousands, probably pushing close to 1 million. It has been not quite 20 years. And the number of programmers has gone from 1 to probably close to 1 million. The number of computers is not quite that large yet. The number of programmers is now pushing something like 1 million. I'm 13 years old at this point. I've gotten my first computer. My mother gave me a little plastic computer. It had 3 bits. I could see 3 ones and zeros in a little window. It was a mechanical machine. It was driven by springs and a crank. But I could still do adds and subtracts and logic puzzles on it. It fascinated the hell out of me. And I got something to work on that dumb little plastic computer, and I knew exactly what I wanted to do for the rest of my life. Wasn't enough. Wasn't enough computers, wasn't enough programmers. There weren't enough engineers and scientists and mathematicians. We still didn't have computer science curricula in university. There was no way to learn this except on the job. And we'd used up all of the engineers and all of the mathematicians and all of the scientists, so we had to get other people to do this programming. Who are those people? Well, we would still draw them from the best and the brightest of, but now that would be accountants and planners and marketing people, anybody with a bent of technical thoughts, anybody who liked puzzle solving. We would go out and try and find these folks, and they were still all old. They were still in their 30s or 40s or 50s, people that we were recruiting from business. They already understood what business was about. Though not mathematicians, they were experienced, disciplined professionals. I imagine Turing would have approved. Maybe not. By 1966, IBM is producing 1,000 IBM 360s a month. That went on for a very long time. These machines were spectacularly powerful in the day. And I worked on a number of these machines over the years. And they're just cranking them out. IBM is just turning the crank and producing 360s. And 360s are getting spread around the country. By 1966, Ole Johan Dahl and Christian Nygaard in Norway had invented Simula 67, the first object-oriented language. It's only been 21 years since Alan Turing, and we have the first object-oriented language. Who programmed in that language? Simula. Two people of importance. Jarnes Drustrup in Edinburgh, and Alan Kay. And Jarnes Drustrup goes on to invent C++, Alan Kay goes on to invent Smalltalk. 1968, Edsger Dijkstra publishes his famous article saying, hey, GoTo might not be such a great idea. Fascinating guy, by the way. Born in Rotterdam before the war, suffered through the German occupation. Came out of that, wanted to be a nuclear physicist. Went to school and saw the very first computer in the Netherlands and fell in love. Thought, this is something I need to do, but it scared him. Because he went to his advisor and said, look, if I start studying this thing, this machine, there's no body of knowledge, there's no science behind it, there's nothing behind it, no one will take me seriously. And his advisor says, well, maybe you will be the one to start that body of knowledge. And he took that as a challenge, and he went on to provide a great deal of that body of knowledge. 1968, Ken Thompson, Dennis Ritchie in the basement of AT&T make 2 remarkable things, C and Unix, on what amounts to a PDP-11. Wasn't actually quite a PDP-11, but it was a mini computer, a transistor-based machine. Those two guys changed the world. C and Unix, which we still use today, in some incarnation or another. In that decade, I just walked through the three major milestones of that decade: functional programming, object-oriented programming, structured programming. Unix, C. A fascinating, productive decade. We haven't seen one since. Not like that. By 1970, the PDP-8s were rolling off the production line. Digital Equipment Corporation. Anybody remember Digital Equipment Corporation? These things are just coming off the assembly line. Right? These lovely little machines. Core memory at first, 4K by 12. We hadn't quite figured out what bytes were yet. 4K by 12. By the time the PDP-8S came along, it was still core memory, but boy, had they shrunk that down. You could buy one of these for $10,000. My buddy and I, we were high school friends, and my buddy and I would sit and look at the catalog of the PDP-8S and think, how are we going to get $10,000? Because that would run Fortran. The number of computers in the world is now exceeding 100,000, probably close to 1 million, growing exponentially. The number of programmers in the world was probably on the order of 1 million, maybe as many as 10 million. Where were we getting these programmers from? Where were these new programmers going to come from? It's pushing 1970 now. We're into the 1970s. Where were the programmers going to come from? Hundreds of thousands of computers, 1 million programmers. Who were they? There's one. That's me. I'm 18 years old. I didn't go to college. I knew exactly what I wanted to do. I found a place that would hire me dirt cheap to write COBOL. COBOL. Very quickly went into Fortran, into assembly language, and never looked back. And I was not the only one. Because there were computer science courses, not quite yet, but you could take an electrical engineering course and you could see a computer. You could touch a computer. You might actually be able to write some Fortran code. There were students in university that could have exposure to these machines. Not a lot yet, but some. And they poured out of university. Tens of thousands of them. And they all had this one thing in common. They were stupidly young and they were almost all male. Why that's true, I don't know, but that seemed to be the case. And I told you this, my first job, there were like 24 programmers and there was about a third of them were women. They were all in their 30s or 40s. About a half to a third of them were women. My next employer, there were 50 programmers and hardly any were women. Something really weird happened right about then. This is a graph that shows what happened to women in computer science. The three green lines are women in the STEM fields going forward into the 2010s. The red line is women enrolling in computer science courses or taking some kind of computer science or course that would lead them to computer science. And look at the inflection point. There must have been an event. I don't know what the event was. A number of people have speculated that it was the personal computer. Right? Personal computer came out right around here. And they say it was marketed to young boys. It was a toy for boys. Now, I don't remember it being that, but that's one of the theories here. I'm not sure I buy that theory, but maybe. One thing was sure, business had to have programmers. The demand for programmers was increasing at a terrible rate, and there were no longer enough people in business to supply that demand. So the young kids coming out of school were a godsend to the business because they were a bunch of very young men, and what they lacked in discipline they made up for with energy, and they were dirt cheap. Got a bunch of kids in their 20s now. They're pouring into industry. And what do? You're a manager now. You're a manager in your 50s. and you're looking at the demographic of your company, and you are seeing the most critical technical resource, the average age of the most critical technical resource is plummeting. Do you trust this? Right? These people who are pouring into your company are going to be the ones who are going to be writing the code that the company absolutely depends on. And you got to be scratching your head going, shit. Up to now, programmers had been disciplined professionals. They'd been in business for a long time. Managers could rely on them. They had relationships with them. They didn't need a lot of management or process. You could kind of turn them loose and say, you know, guys, figure this out. We trust you. They knew how to manage their time. They knew how to communicate and work together. They understood deadlines and commitments and what to leave in and what to leave out. They got all of that. But now, hordes of young men were tearing into the industry. Those original people had worked absolute miracles. The IBM 360 virtual memory operating system, the very idea that memory did not need to have fixed addresses, that programs did not actually have to be in memory permanently. All of that stuff was invented by those. NASA had the Mercury space capsule software, the Gemini space capsule software, the Apollo space capsule software, all that stuff had been done. Structured programming, functional programming, object-oriented programming had all been discovered by then. We had Fortran, we had COBOL, we had Algol, we had Lisp, we had C, we had Unix, all done by those 30-year-olds and 40-year-olds and 50-year-olds who were the original cohort of programmers before the 70s came along. Those original programmers knew how to get big things done. And what process did they use? Well, I don't want to call it Agile because that's not quite right. They didn't use that term. However, it has been said that Agile is the process used by programmers in the wild. But hordes of young testosterone-driven boys need discipline imposed upon them from above. They need close management, they need process. And what better way to impose that than something like waterfall? Now, the waterfall paper, the paper that described the waterfall process, was written by a fellow whose name was Winston Royce. And he wrote it in 1970. He wrote it in 1970. And he wrote this lovely, lovely paper. I wonder if I've got an image here. Oh yeah, I do, right there. He wrote this paper, and in this paper he put this image. And he talked about what it was about. You know, first of all, you got to get the requirements, and then you got to break them into software requirements, and then you analyze it, and then you design it, and then you code it, and then you test it, blah, blah, blah. On the next page, he had a different diagram. I don't know if I've got that here. No, that's okay. He had a different diagram, and the different diagram said, that doesn't work at all. We tried that. That doesn't work. What you have to do instead is this is going to fail here, and you're going to have to go back to the coding and redesign things. You'll have to reanalyze things. And he put all these back loops in. And then on the next page, he actually tore that apart and said, even that doesn't work. You just have to do it all at the same time. So it was a very interesting paper, which apparently nobody read. Because this is what was pushed on us in about 1970. And I remember this event. I was a young programmer at the time, and I remember when that picture showed up in the trade journals. We didn't have Facebook, we didn't have, 4chan or anything like that. We didn't have any electronic network, but we had magazines. And these pictures started showing up, and it was a godsend. It was terrific. We wanted this. Because imagine how powerful it would be if you could analyze things and know how long it would take you. And when you were done, you would know you were a third done. And then you could design things and you'd know how long it would take you. And when you were done with that, you were 2/3 done. What a wonderful idea. It's now 1970. And the waterfall era has begun. And I theorize in this talk that it began because of the influx of undisciplined young people into the field. And it lasted for 30 years. Now, how long did it take to get to the waterfall era? 46 to 70, 24 years. It lasted longer than that. The waterfall era lasted even longer. How many programmers in the world today? Right now, how many programmers are in the world? Yeah, I mean, that's right. It's like, I don't know. Well, okay, it's a lot. How many? Well, could it be 10 million? Yeah, it's 10 million. It's easily 10 million. Could it be 100 million? I suppose it depends on if you count the VBA programmers. But let's use that as a number. 100 million. Might as well use that. It's a reasonable number. Okay, in 1946, it was 1. In today, 2019, it's 100 million. That's 73 years. How do you get from 1 to 100 million in 73 years? What kind of growth is this? Is it linear? It's not linear. It's exponential. It's got to be exponential. It's the only way you get to 10 to the 8th in 73 years. Okay, well, if it's exponential, we can use 2 as the base of the exponent, and we can establish a doubling rate. Okay, so how many doublings does it take to get from 1 to 100 million? Okay, a million is about 2 to the 20th. 128 is 2 to the 7th, so 2 to the 27th is about 100 million. Okay, 27 doublings. 27 doublings in 73 years is a doubling every 2 years. The number of programmers in the world double every 2 years. Chills should be going down your spine right now. Right? Does the number of programmers in the world double every 2 years? Is that what's been going on? And the answer to that is probably not, because in the first decade, the doubling rate was much higher than that. The first day was Alan Turing. The first week, there were 10 guys. The first month, there were 50 guys. The doubling rate was very high at first. It slowed down after the first decade. What did it slow down to? And there's plenty of evidence to suggest that it slowed down to once every 5 years. That the doubling rate now is 1 every 5 years. What does that imply? It implies a number of very interesting things. Number one, it implies that half the programmers in the world have less than 5 years experience. And this will always be true as long as we are doubling at a rate of once every 5 years. Half the programmers in the world will have less than 5 years experience, which puts our industry in a state of perpetual inexperience. Number two, there aren't a lot of old people. People often suggest that software is a young person's discipline. And why do they say that? Well, because there's so many damn young people. And they ask, well, where did all the old people go? They must leave, right? They just don't stay because old people can't do this. No, we're all still here. There just never were very many of us. How long can we keep going at this rate? Doubling every 5 years. Has the demand for programmers slowed? No, it hasn't. So in the next 5 years, we'll probably see another doubling. The only time the demand for programmers ever slowed that I know was at the dot-com bust, and it only slowed for a year. And then it just picked right back up again. The demand for programmers continues. The hardware's changed like crazy. The hardware's gone through a nutty expansion. How many transistors are in this? Over a trillion. Over a trillion. More than 10 to the 12th transistors are in this thing in my hand. Imagine they were all vacuum tubes. How much space? How much space would it take to hold a trillion vacuum tubes? This math has been done. There's a fellow who did it. His name is Jack Gansel. He writes a column for the EE Times, and he did the math on this. He said, if you wanted to have an iPhone made out of vacuum tubes, it would require a building that had the volume of 170 vehicle assembly buildings. The building at NASA where we built the moon rockets, right? The biggest enclosed volume in the world. 170 of those. It would weigh as much as 2,500 Nimitz-class aircraft carriers. The amount of power consumed would be well over 1 watt per tube because the tubes had a filament in them. And that means that we would need at least a terawatt of power simply to power the damn thing, forcing us to build 500 2 gigawatt power plants, the biggest power plants we make, nuclear power plants. Right? And it would cost on the order of $50 a tube. $50 trillion, the economic output of the world. And once you had built it, there would be no one to call. I hold in my hand the economic output of the world in 1950, and we give them away for your signature on a 2-year contract. If you want to buy one, they will cost you less than $1,000. That is an astounding achievement. The number of orders of magnitude involved with that change I have lived through. I have seen all of the changes from vacuum tubes to this. The first computer I worked on had vacuum tubes in it. Now I work on these things. What's happened to the software? Damn near nothing. Damn near nothing. Oh, we've got great tools. Who's using IntelliJ? You know, the JetBrains guys. Magic. It's just magic. The stuff you can do with but that's all based on the hardware. The fact that we've got enough power. You know, we can do Angry Birds. I mean, that's just amazing. We couldn't dream of that in the 60s. We did dream of it. We dreamed of it in the 60s. So wouldn't it be cool? But we could never get there. We didn't have the computer power. But what's happened to the software? Well, simple example. I could take a programmer from 1968. If I had a time machine, I could go and get a programmer from 1968 and transport him and put him in front of IntelliJ and ask him to code Java. That person, who would probably be female, would need 24 hours to recover from the shock. But then they would be able to write the code. Because what is the code? Well, if statements, while loops, assignment statements, just code. Same code that they were writing before, in a better place. I could take you, and in my time machine, I could transport you back to 1968, and I could put you in front of a PDP-8 and show you how to program in assembly language using paper tape and a teletype. You'd need 24 hours to recover from the disappointment. But you could write the code, because the code hasn't changed. The code is the same. What revolutions have occurred in software since 1968? In the 60s, we had the object revolution, we had the structured revolution, and functional programming was the first of those to be invented. We're only now going through the functional change. But functional programming had existed long before. What revolution has happened since? What massive change has happened to the stuff that you and I manipulate with our hands? The internet. Did we have the internet? When was the internet invented? It was the 60s, mid-60s it was invented. They got the first internet message passed around in the 70s. It was a defense thing, right? Defense department. And an internet node had 6 computers in it. It was tough to get those going in those days. Were there networks before the internet? Yeah, there were electronic networks before the internet. Anybody remember IBM green screens? Remember those old green terminals that people would type into? Those networks were everywhere. They weren't very fast. They weren't great. But there were networks. And even if we didn't have networks, we had distributed computers. Because we had computers that we could wire together, and we could send data across buses. We knew, even in the 60s, we knew that computers would be talking to each other. And you can tell that by looking at the movies from the 60s. Anybody remember the Fortran project? Anybody see that movie, the old movie, the Fortran project, where one computer takes over all the nuclear weapons of the United States and another computer takes over all the nuclear weapons of the Soviet Union, and then they hook phone lines between them. The two computers work out how to call each other over phone lines, and they invent their own language. Go watch that movie. That's a terrific movie. The Fortran project, it was called. No, I'm not going to talk about that. I'm not going to talk about that. I'm not going to talk about that. Oh, I will talk about this. How many of you are doing test-driven development? Ooh, okay, some of you. Good, good. Some of you. I also see a little of this. Okay, all right. What's the matter with the rest of you? One of the things that Turing said was we are going to have to maintain appropriate disciplines. What appropriate disciplines do you maintain? Do you have a set of disciplines that you can name, that you can write down, that you can follow? Like a doctor will have a discipline washing their hands. You know how a doctor washes their hands? You know, they don't just go in there and wash their hands. Right? A surgeon will go in there and they'll get a special brush and a special soap, and then it's 10 strokes across the side of the finger, 10 strokes across the top, 10 strokes on the other side, 10 strokes across the face, and 10 strokes across the nail. Next finger. They have a discipline. They better have a discipline, because they're going to kill people. Got to have a discipline. Do you have a discipline like that you can write down? You and I are scribes. We write arcane documents. And these arcane documents, every symbol has to be right. If there's an error on one of these arcane documents, then terrible things can happen. People can die, fortunes can be lost, the business can lose money, you could get fired. Terrible things might happen if there's an error on these funny documents with weird symbols on them. Who else has that problem? Who else has that kind of problem? Not software developers, somebody else. Accountants. Accountants have that problem. Accountants make weird documents with funny symbols on them. No one understands them. Every symbol has to be correct. And they're complicated, and they're distributed, and they're isolated, and they're modular, and they've got all these books, and the money flows this way and that way and around and over, and every symbol has to be right, otherwise terrible things happen. And we've seen some terrible things happen. I could mention Enron. How do the accountants do it? They have a discipline. They can write this discipline down. They know this discipline. It has a name. It's called double entry bookkeeping. They enter every transaction twice. Once on the asset side, once on the liability side. They follow separate mathematical pathways until there's a single subtraction on the balance sheet that must yield a zero. And the way they enter the transactions is one at a time. Transaction on the asset side, on the liability side. Do the sums, zero, good. Next transaction, asset, liability, sum, zero. Good. Next transaction, asset, liability, sum, zero. They're taught to do that in school. They do not enter all the assets, enter all the liabilities, sum it up, 137. They don't do that. Test-driven development is double entry bookkeeping. It's exactly the same discipline. It's done for precisely the same reason. Everything is entered twice. Once is a test, once is production code. They follow complementary execution pathways until there is a zero. Zero tests failed. And we do it exactly the same way. A little bit of test, a little bit of code, execute zero. A little bit of test, a little bit of code, execute zero. Same discipline, same reasoning. For accountants, it's a matter of law. If you don't use double entry bookkeeping as an accountant, you go to jail. We haven't put anybody in jail as a programmer yet for not doing test-driven development. But you are laughing at that, and you should not be laughing at that, because we are killing more people than accountants are. The day will come, and it's probably not too far away. Some poor software kid's going to do something stupid, kill 10,000 people, maybe 100,000. It's possible. And you could easily imagine what that might be. Some disaster of some kind. And the politicians of the world will rise up in righteous indignation, and they will point their finger at us. And you'd like to think that, no, they're going to point it at my boss. They're not going to point it at me. I'm just a programmer. But we saw what happened when the politicians of the world pointed their finger at the executives at Volkswagen. Anybody watch the testimony of the CEO of Volkswagen North America as he testified before the American Congress about why Their software in their cars was cheating the Environmental Protection Agency in California. Did anybody watch that testimony? How could you have let this happen without establishing ethics, without establishing disciplines, without establishing practices? How could you have let this happen? There are lives at stake. There are fortunes at stake. How could you have let this happen? And if our answer is, well, my boss told me it had to be done on Tuesday, that's not going to fly. And the politicians of the world will do all they can do. The only thing they can do is legislate. And they will tell us what languages we have to use, what platforms we have to use, what books we have to read, what processes we have to follow. I would like to avoid that. And the way we avoid that is to do what the doctors did. Get there before the politicians do. Establish the rules first. Establish the ethics first. Establish the disciplines first. So that when the accident occurs, and it will occur, it doesn't matter, and the politicians point their finger at us and say, hey, how could you have let this happen? We can respond by saying, look, here are our disciplines. This is how we enforce it. This is how we behave. This is our ethics. This is our professional oath. This was a terrible accident, but it was not because we were negligent. And we could not say that today. And I'll leave you with that thought, happy as it is. Any questions?
Yeah.